My name is Denis Sladkov. I'm a lead rendering programmer at Saber Interactive, and today me and my colleague Anton Krupkin, Saber's founder and CTO, will talk about some behind-the-scene rendering details in our upcoming game World War Z. World War Z is a 4-player cooperative third-person shooter inspired by the Paramount Pictures movie of the same name. As you might remember, huge zombie crowds were one of the main hallmarks of this movie, and that's the unique feature of the game as well. In this game, players are continuously fighting through the hordes of fast-pacing zombies. There are a lot of these zombies around, and that requires players not only to shoot for themselves, but also to carefully plan and coordinate their actions. Such kind of game design with hundreds of active characters demands quite a lot from underlying technology. And today we will show how, using our in-house engine, we were able to render such complex scenes. Game will be released next month for both major consoles and PCs simultaneously. Our console version targets 30 frames per second with up to 4K dynamic resolution. PC version will run using one of the two major graphics APIs. DirectX 11 is our baseline compatibility version, and Vulkan is the most optimized version for modern machines. I would suggest to start with a small gameplay trailer, just in case some of you guys haven't heard about the game, and to give you some of the context about the things that we will talk about today. Okay, so here's the plan for this talk. At the first part, I will talk about our engine and rendering pipeline architecture. I will start with a high-level GPU frame structure. Then I will very briefly describe some of the shading techniques that we use. And I will say a couple of words about Vulkan optimizations that we did. That part is intended mostly for engineers. During the second part, Anton will talk about zombies rendering, mostly from the technical art standpoint. So if you are a technical artist, so please don't be bored by the first part and don't go too far away. Anton will start with close-up zombies, which we can render hundreds of, and that's actually most of the zombies that was presented in this trailer. Then he will explain how we render thousands of zombies on the far plane. And finally, he will talk about our gore or jibbing system, which was also demonstrated in this trailer, but okay, it's about tearing zombies apart. Okay. As I said before, we are using our own engine. It has a pretty long history, with the first game, Wheel Rock, released more than 15 years ago. Since then, a lot of titles for a different generation of consoles and PCs were released using this engine. World War Z is using the latest generation of our technology, and we will talk about that today. Here are the main ideas behind our rendering engine. We are using GPU-driven visibility system. It does frosting and occlusion culling for the whole scene, and results are then read back by CPU. Shading-wise, we are doing rather usual forward plus. Dynamic lights and reflection probe volumes are rasterized into camera space voxels, which are then used in forward pass shading loop. We are also doing full Z pass, not only to eliminate overdraw from heavy forward pass, but also because we are doing some of the pre-shading steps based on Z-pass data. I will talk about them in a minute. We are using directional light maps for global illumination. They are basically in RNM or half-life to basis format with some additions to better handle specular highlights and reflections. If you're interested in more details about our light maps or how we build them, I encourage you to visit another GDC talk by our engineer Max Gridnev this Wednesday morning. Our current engine architecture implies 2 full frames of latency. That's a rather classical scheme where game update loop run simultaneously with the previous frame rendering, and the GPU running slightly behind all of this. Because of some tight GPU and CPU synchronization applied by our visibility system, we need to feed GPU as fast as possible, so we are heavily relying on multi-threaded command buffer recording, which is efficiently supported by Vulkan API. So let's now walk through the single frame of our GPU work. We will follow this job graph in several steps in a timeline manner. Green blocks here are rasterization jobs, yellow blocks are compute jobs, arrows are data dependencies, and horizontal offset of each block determines its order of execution. Our first step is full geometry Z-pass. All opaque geometry rendered here from in front to back order. Besides depths, we are also writing wall space vertex normals. This pass is almost stateless. There are no textures, no complex shaders. It's designed to be as fast as possible for both CPU and GPU. After Z-pass, we are doing some pre-shading tasks. That way, we offload a significant amount of work from our heavy forward plus shading pass. And that also allows us to use all kinds of screen space optimization for these steps, like rendering some of the terms in lower resolutions, or use screen space blur techniques and things like that. For shadows, we are using ordinary PCF shadow maps. We support up to 4 fully dynamic shadow mapped lights per frame. For directional light sources, we are using parallel split scheme with up to 3 splits. So each shadow map split is first rendered into the shadow map, then corresponding that buffer region is marked with stencil, and then shadow factor is written to one of the channels of full screen for channel shadow mask, which you see on the screen. Up to 12 Poisson disk PCF samples used for filtering. We are also rotate this Poisson kernel per pixel with 3x3 screen space jitter mask, and depth-aware blur kernel of the same size is applied to the whole mask afterwards. Each shadow map split is also stored into the fixed resolution shadow map atlas to be later used by transparent geometry. After that, during our forward pass, we are sampling our indirect lighting from light maps for static geometry and from light probes for dynamic objects like character or vehicles. We are using second-order spherical harmonics for our light probes. All this indirect lighting is then multiplied by occlusion term and combined with direct lighting, which is built from our pre-computed shadow mask and all the material data which is available in forward pass. Transparent objects uses this Froxel structure to cycle through all affecting lights and sample shadow maps with simple 4-tap PCF filter. So let's now talk about occlusion term in our engine. Large scale, high quality static occlusion is pre-computed into the light maps, but this way we have an obvious problem with dynamic objects like characters on the screen. They appear like floating around in places where they're not grounded by some direct light shadows. So screen space ambient occlusion helps a bit with this situation. It provides us with some small scale contact between static and dynamic geometry. Our SSAO implementation also uses vertex normal from ZPass as a kind of importance data to better distribute the buffer samples. But that's still not enough. We always wanted something more, something like soft shadows from indirect lighting, for example, skylighting on this shot. And for that, we are using so-called capsule shadows. The idea came from Last of Us presentation from SIGGRAPH 2013. A set of capsules attached to character skeleton, and each capsule casting ambient and directional occlusion terms. Directional occlusion term uses dominant light direction, which is automatically extracted from our global illumination light probes. So this way we have pretty good contact shadows for characters without introducing additional cost of shadow mapped lights. This occlusion term is used to mask all indirect lighting and summary reflection term in our engine. For reflections, we use a rather standard combination of cube map probes and screen space reflections. Probes are basically the boxes placed throughout the level by artists. For each box, cube map is automatically captured, and all cube maps for the level stored as a single cube map array texture. During the beginning of the frame, each visible cube map probe volume is rasterized into camera space Froxel grid, with each Froxel storing up to 8 8-bit indices of all affecting cube maps. That data is later used to index into our cube map array and to fetch the reflection data using per pixel normal and roughness, which is available in shading pass. For our screen space reflections, we use a rather standard algorithm which runs in half resolution. Temporal sample distribution allows us to have enough samples to represent kind of blurry reflections, but some amount of ghosting is an unavoidable trade-off here. Another visually important feature of this game is volumetric fog. This is how it looks. So in this pass, we are rendering box-shaped fog volumes into the half-resolution buffer. Each volume has its own density distribution function and may be linked to a light source. For each pixel, we are merging array through the volume with up to 24 discrete steps, and we sample shadow map and density function pre-calculated integral during each step. For this technique, we are also using screen space dithering. This time we use it to slightly offset ray marching sampling points for each pixel, and then as in shadows, full screen depth-aware blur used to hide these dithering artifacts. So we ended up in our most heavy-weighted forward plus shading pass. Huge shaders, a lot of resources, it's all being merged here. Output of this phase is fully shaded HDR opaque scene. And we are also writing a small G-buffer here. For example, we are writing velocity to be later used by our motion blur or temporal anti-aliasing color clamping logic. And we also can write some kind of specialized data to this G-buffer, for example, for skin blur or some other custom post-processing steps. And there is another important job which runs before our forward plus shading code. That's our visibility system. As you remember, we are on CPU, we are always rendering previous frame while game update loop works on next frame. So at some early point during game update loop, we fetch user input, and basically we have all the data to set up a camera for the next frame. So it's possible at this moment to kick a GPU visibility test for the next frame just in the middle of rendering previous frame. But we want this job to run as early as possible on GPU because we then wait for this data to be able to start writing next frame Z-pass on CPU. So therefore it's placed before our forward plus pass. Our GPU visibility system is basically taking a whole bunch of B-boxes, one B-box for each scene object, and then checks if it's visible from each of the given frustums. It uses a hierarchical depth buffer test for occlusion culling for the main camera, and shadow map cameras go through simplified test. They're just checking B-box versus frustum. It's a very simple system, runs pretty fast, just under 0.7 milliseconds on Xbox One GPU for our pretty big scene with more than 100,000 objects. But that system requires, as I said, one extra frame of latency for CPU readback. Let's look at the particular example. For example, this is one of the random spots in one of our biggest scenes. Japan scene. There are not very readable statistics here, but it's basically said that about 8% of the scene is visible from this point. Here are the manually altered occluders, which are rasterized into fixed resolution depth buffer, and that depth buffer is then hierarchically downscaled down to 2x2 resolution. And then each particular object's B-box screen extents are used to choose a MIP level from that hierarchy and to do occlusion test. Here's the same spot from the outside. That way our artists can visually check the efficiency of their occluders. Okay, so after our forward shading pass, we are rendering transparent objects and special effects. These are basically rendered in back to front order, using some of the data saved from shading prepasses like Shadow Map Atlas and Froxel data. Then we are doing motion blur, temporal A, and end up with full resolution UI rendering just right after the time mapping. That's all pretty standard stuff, and I will not go into details here, but if you have any questions about that, feel free to ask me after the presentation. We have a couple of heavy rasterization-bound steps in our pipeline. That's Z-pass and shadow map rendering. And with the Vulkan API, it is possible to better utilize compute units during these stages using async compute queue. So we are interleaving all occlusion and Froxel mask computations with shadow maps. but Z-pass utilization wasn't so obvious. But in Vulkan, it's possible to actually fire a present from the async compute queue. So we were able to interleave next frame Z-pass with our post-processing frame tail. But to be able to do it, we have to remove UI rendering, which is a rasterization-based job. So we just pre-render UI into separate texture and merge it in compute queue just before the present. Overall, I would like to say that going from DirectX 11 to more low-level API was a worthwhile investment. At the end, we got only slightly better GPU timings, but CPU savings were significant. And resource memory aliasing not only saves sizable amount of that memory, but also opens the road to simplified console-style dynamic resolution scheme for PCs. So that's basically all I have to say. And now I will step down and give a word to Anton, who will talk about, I suppose, less boring stuff. Thank you.
All right. Hi, everybody. My name is Anton Krupkin, and now let's talk about fun stuff. Let's talk about zombies. So, in our game, we feature a lot of zombies on screen. More than 5,000 zombies per frame. Although, most of them are non-interactive zombies. We call them background swarm. And only 300 or so zombies can be actually killed, can be interacted with. And of those 300 zombies, only 50 are fully grown zombies with brains. And those zombies do actually attack you and run towards you. So in order to render such great variety of zombies, we had to rely heavily on instancing system. But at the same time, we needed to create a very flexible customization system to make sure that no zombies are looking alike. So on this screen, you see 300 foreground characters. And as you can see, there is very little repetition. You pretty much don't see similar characters on screen. Similarly looking characters on screen. So how do we do that? Let's talk about zombie customization. The major part of zombie customization system is geometry customization. So we chose to create 3 base archetypes or 3 skeletons for our zombies, like male, female, and big male. For each archetype, we decided to have 4 different regions. Apparent regions are legs, torso, head, and hair or hats. And for each region, our artist created 4 to 8 mesh variations. In total, we got about 70, more than 70 different combinations for each archetype. Here, in this example, you see the mesh variations for like standard male archetype zombie. As you can see, all the textures are on the gray side. Why? Because we need to also customize colors for zombies, colors and stains. So how do we do that? Let's look at the other slide. So to customize color and stain masks, our artist created special masking textures. One masking texture for color, it's 4-channel texture, low res, and one masking texture for stains. Also, all zombies share texture array with stain textures like blood stains, snow, dust. In this texture array, we store albedo, normals, and roughness textures. And in runtime, it all comes together when we supply on per instance basis solid colors and channel masks for colorization, and channel masks and texture array indices for staining. Let's look at how it works in practice. So we start with grayscale, almost grayscale zombie. Then we colorize like pants and hoodie in this case, in different colors. Then on top of that, we colorize the t-shirt and boots. Then we add blood and dirt masks on top. Dirt stains and blood stains, and then we add snow stains in case zombie is running in a snow level. This all together allows us to create hundreds and hundreds of distinct looking zombies. All right, now we know how to create this crowd. How do we render this zombie crowd efficiently? And make sure that this colorization and make sure the customization of zombies does not introduce a lot of inefficiencies in our rendering. So first, as Denise pointed out, we use visibility system to call all zombies, and we discard the zombies that are not visible. So for all visible zombies, we collect identical meshes into buckets. And then once we collected identical meshes into buckets for all the scene, we process those buckets and create so-called batches. So how do we do that? First, we take each bucket and sort this bucket by visibility mask. What's visibility mask? Each camera that passes through visibility system has its own bit in this mask. So essentially, we sort bucket and we, for example, separate meshes that are rendered like into one camera or into two cameras or into like all kinds of combinations of cameras. Then after that, we gather identical meshes with identical visibility masks into batches, and for each batch we fill constant buffers with instancing data, and then for each batch we generate several draw calls, and put those draw calls into our render queue. Draw calls for Z-pre pass, for shadow map pass, or for shading, or for distortion, for example. This slide shows the sample workload to render 300 zombies. For example, zombies that are in LOD 0, they render it into 26 batches, and for example, 100 zombies that are in LOD 4, they're stored into 52 batches, for example. And total we get 223 batches, about 600,000 triangles for all the zombies. It takes about 2.5 milliseconds for all 6 threads of CPU to generate all this data and to pass those batches and convert those batches into 1,000 draw calls. So all in all, 300 zombies are rendered into, we use about 1,000 draw calls to render those 300 zombies. Now, we know how to render foreground zombies. What about background? On background, we have a lot of zombies, over like 5,000. But I mean, why 5,000? Because we never needed more, I guess. But those zombies they're not interactive. Essentially, it's a GPU-driven animation. For those zombies, we use only 8 different variations, 2 mesh types and 4 different textures for those mesh types. For those zombies, we utilize our existing grass rendering solution, and we add to this grass rendering solution. We add only vertex animation for zombies and the motion along pre-modeled paths for those zombies. So, what's a grass rendering solution? Our artists, they paint those zombies essentially like glass blades in level. And then those zombies, they merged into containers, and each container contains everything that you need to cool and render the bunch of zombies with single draw call. So then we bake vertex animation for those zombies. So essentially, how do we do that efficiently? We limit ourselves to just one single running animation, because it's a zombie swarm, it's running in the distance, it's running somewhere, and you don't really get to see this running animation. Since we only have 2 different geometries for zombie swarm, so we bake two different running animations. This running animation is stored into 2 32-bit textures. One texture encodes offset from default, and this offset is quantized into 8-bit. And the second texture has object space normals. And in runtime and vertex shader, we sample those textures with vertex ID and frame number and get our frame of animation. So how do we move zombies along predefined tracks? Again, our level designers, they author those tracks as splines. Each track then quantized, stored in, and all the tracks are stored in the single 2D texture. And then in vertex shader, we sample those tracks with elapsed time and track index, and we get our position of zombie on this track. All right, now comes the movie. I do sincerely hope it won't crash. Oh. All right, that's how zombie crowd looks like. Zombie swarm. As you can see, even from this distance, you don't see much of a repetition. You don't see the penetration of zombies through geometry. All right. So now we know how to render so many zombies. What do we do with zombies after we render them? Like, we need to destroy them somehow, right? So let's talk about gore system in the engine. On a high level, the gore system works the following way. So whenever we wound somebody, the wounded region gets hidden. And then pre-model gore mesh gets placed in place of the hole. And then we put runtime decals to hide the stitching between pre-modeled meshes and the original mesh. So here you see on the screenshot, you see different regions that can be jibbed from living zombie. How do we do jibbing exactly? Our artists paint per vertex masks for regions to be hidden. Each mask is 1 bit, 32 regions max per character, and we have to split vertices on edges that share different regions, and we duplicate vertices there. And then in runtime, all we need to do is apply one 32-bit mask, and from there we can determine which regions are hidden, which regions are visible. Then we do culling in vertex shader, essentially create zero area triangles, and those triangles get called by GPU. And on this screen you see jib measures that we place in place of holes. And that's a set of GIP meshes for this particular mesh customization. All right, and then on top of all that, we need to place decals, right, to create blood stains and hide the stitching. So how do we do decals, for zombies? Whenever hit is detected, like bullet wound or explosion damage, we transform this damage into regional bind pose of the model, and then we store it for each model. Then we, in runtime, we pass bind pose vertices to pixel shader, and in pixel shader we run loop over all the decals up to 16 decals max. And we can do it efficiently because we use only planar projections and simple blend modes. But those decals, they able to modify albedo, normal, and roughness and metalness. And it's all done in forward plus shader before we apply lighting. All right, let's see how it looks in the game. All right, thank you very much. And special thanks to guys from AMD who helped us with Vulkan. And special thanks to the team who put a lot of hours into developing the game. All right, any questions?
Let me try to start the video maybe.
Hi. If I understand everything correctly, you generate all your zombie draw calls on the CPU. Is that correct?
Yes.
Did you consider multi-draw indirect? Did you experiment with it?
Yes. The question is whether we considered moving draw call generation and using indirect drawing
Yes.
functionality. With this advanced customization system, I don't think it's practical and feasible to generate those draw calls on GPU. Why? Because draw call generation takes very small amount of time comparing to animating zombies, zombie logic, pathfinding, and ragdolls. So the game is pretty CPU hungry, but we don't spend that much time generating draw calls. We just use instancing. We keep a number of draw calls under 3000 per frame, and we use Vulkan to optimize common buffer generation, and that's pretty much it. And we are within our budgets, time budgets.
Okay, thank you.
Welcome. Right? Questions?
I wonder that you're talking about keeping user original match tessellation. I don't understand how tessellation do here. What does tessellation do here? What's keeping? On the region, what is masking the page? I think it's the last two page, I think.
Could you please repeat the question? I'm sorry.
I don't understand how tessellation were here. Tessellation.
Tessellation?
Tessellation is the pipeline tessellation or other meaning?
Do we use tessellation in there?
Yeah.
No, we don't use any tessellation. I mean, we use tessellation for things like water. We use tessellation for particles.
Not for zombies.
Okay. Not for zombies.
Let me answer if I understand you correctly. You are asking about mesh region hiding, right?
Oh, yeah.
So we are basically using our original installation of this mesh. So LOD 0 is about 15,000 triangles already. So unlike the guys from Valve did it some time ago, we're pretty happy with this level of tessellation, which is already modeled. So we can just use original topology to decouple a couple of part of meshes. So we don't use any tessellation here. We just use original topology and just decompose it into different pieces.
And we do not split geometry in runtime.
Okay.
So
yeah,
it's all pre-split and marked by artists.
Okay.
Because there is no runtime cutting. I mean, I remember our first game had that, but since then we are not using it anymore. Long time ago.
Hi. How do you? Anyone else? How do you manage collision with all these objects? I don't know if you talked about that, but
collision for
collisions
zombies?
for all the zombies. Like, are you doing it in the CPU after?
All the collision is run through Havoc. So we do the pathfinding and collision using Havoc ragdolls and Havoc animation and Havoc AI. But we employ a lot of different tricks on top of that, because when you throw like a grenade into a swarm of zombies, you can't have 50 ragdolls flying. The performance will deteriorate very quickly. So what we do, we employ all the usual tricks. We sparse, we put a lot of particles, we jib, and those jibbing pieces, they just disappear. And we put only maybe 5 different bodies through full collision.
So one more follow-up question. So how about imposter rendering? Would that help in rendering these zombies? Imposter rendering?
Imposters, yeah. That's one of the options for sure. You mean for zombie swarms, for huge swarms. But this technique that we described is just sufficient. You pay essentially only for vertex processing there. And given the numbers, about several thousands of zombies, so you can just use very low res meshes there.
Okay.
And actually this kind of geometry animation looking better and easy to alter as well. So you don't have to write some customized imposter rendering with animation, frame blending and things like that. That kind of approach, which was like implied, first used by the Uncharted guys, actually that works pretty well and very cheap in implementation.
Yeah.
And it can be used for many different things, not only for zombies, for any kind of background activities, which is perfectly perfectly fits into existing rendering pipeline. For example, you can render all the stuff into the shadow maps and get like correct shading without any additional effort.
Mm-hmm.
So it's just simple as that, and it works.
Okay, thanks.
So we didn't bother with this billboards or stuff like that.
You mentioned that the animation is baked, and therefore, like it's already skinned. The skin is applied to the mesh and the skeleton. So what happens when you take out a chunk of that mesh and replace it with a different one? Like, does that not mess with the skeleton?
Okay. Okay. I can answer that. So essentially, when we take out the chunk, the skeleton is still there. The geometry is still there, just not visible. It's been animated. So we take out chunk, we pop the bloody plug into the place where the chunk was taken out, and then we spawn the chunks which just took out as a separate entity with separate collision and separate animation.
Okay.
So essentially, if you see a leg falling out, that's another entity spawned. If you see leg disappeared, it means that this geometry just is just hidden. That's
okay.
it.
And I mean, when it's like a one-on-one basis, that's like easy with overdraw. But what if there's 50 zombies that you're damaging, like with a grenade?
And then we just limit the number of body parts flying around.
Okay, but I mean, like when it comes to overdraw, like they invisible. Are they alphas? Like, does that not?
No,
hurt?
it's not. It's not alphas. Essentially, this geometry gets discarded by GPU because it's zero. We make it zero area like all those triangles, zero area triangles.
All right.
So we pay the cost of vertex processing, but there is no pixel processing involved, no overdraw.
Okay, thank you.
No. All right, thank you very much.
Thank you.